Okay, welcome to your Chapter 9 introductory video. This chapter is on thermochemistry. Really, we can think of this as energy changes associated with chemical reactions. As you might have thought about it, chemical reactions might gain or lose energy over the course of a reaction, and that can often be measured by temperature. So several things we'll learn about in this chapter. It really is all about energy. Let's say we have a reaction. We have A plus B going to C. We might say that energy is in fact released with this reaction. So it would be written on the product side. We don't always write the energy as a product, so what we'll do is something more like this. Effectively, we'll say, for instance, that the energy associated with this, let's say, is negative 802 kilojoules. This would mean 802 kilojoules of energy has been given off. It's been written off to the right there. And one thing you should recognize is the fact that if I were to reverse this reaction and say C goes to A plus B, then that in fact that the energy of that reaction would actually be the reverse of that. Exact same magnitude, but reverse. One would be negative, one would be positive, in the sense that the first reaction is giving off 802 kilojoules of energy and the second reaction is absorbing it. Another thing you might realize is if I were to take this first reaction and multiply it by a factor of 2, well, since energy is going to be an extensive property, it's going to be dependent on the amount of material, and therefore the delta H now, we call this delta H, we haven't introduced that yet. So the energy associated with this reaction now will in fact be a negative 1604 kilojoules. So anything you do to the reaction here affects the energy associated with that reaction. And that's a lot of what this chapter is going to be about. Another point I want to make is that, say, for instance, you want to know what the energy is to go from A, which is here on an energy profile, if you look at this as energy, to D, to here. And you don't know it. But what you do know is the energy going from A to B here, and you also know the energy going from B to D. Effectively, we can now determine what the energy is going from A to D simply by adding these two values. And you can see that this one would say, if we look at it like this would be, say, positive 800, and this one would be negative 700. You could see that it would take 800 joules of energy, if you will, kilojoules of energy, if these are in kilojoules, to go from A to D. So what you can use is chemical reactions, and you can manipulate them in different ways. You can reverse them, you can multiply them by a factor, and add them up, and ultimately get to the reaction that you're interested in, this A going to D. That's really the heart of this entire chapter, and that can be done through what we call formations, Hess's laws, and just manipulating chemical reactions. So the learning goals for this chapter, then, you're going to master stoichiometric calculations involving energy, and we're going to focus on heat enthalpy. And obviously, what I mentioned to you before, you got to know your stoichiometry. Familiarize yourself with heat capacity and be able to perform related calculations. So we'll define this and talk about this. Use calorimetry concepts to calculate enthalpies of reaction. This is a method that we can use in the laboratory to help us determine what the energy is associated with a chemical reaction. Once again, as I mentioned, we can measure temperature, which is the amount of heat absorbed or gained by a chemical reaction. There's Hess's law that's going to allow us to manipulate reactions and calculate enthalpies of new reactions. And the last one is just be able to recognize what formation reactions are. So here is the chapter outline that you'll be covering. We'll be covering in the lecture, and I'll touch on several of these. So here's a particular energy profile here, and it's just showing you this particular reaction. It's hydrogen gas plus oxygen gas goes to H2O. And it's showing you that energy is released. Why? Well, because we think of this here as a y-axis, so these are higher values than these down here, and that the energy is dropping over the course of going from reactants to products, so energy is released. So this is just an energy profile reaction. You get the reverse reaction, the energy would be this right here. You all know about conservation of energy, but a couple terms we need to define related to that energy is the system and the surroundings, and then the universe, if you will. The system is the part of the universe that the focus of the thermodynamical study you're making is. And that is your reaction chamber in the lab, or in the kitchen, what you're cooking, or whatever you're dealing with. That is your system, okay? The surrounding is everything in the universe that's not part of the system. And your system can be isolated, open, or closed. I'll define that. Universe is basically everything else. These are just terms to be defined. So these are your systems right here. Isolated system. This is a thermos, so what we're saying is that heat is not exchanged with the environment. So it's very difficult and almost impossible to have a truly isolated system. But we say that something like a thermos is isolated because there's very little heat exchange. It's very slow. It takes a long time to lose heat. A closed system, the picture in your book, I believe this comes from, is not really accurate. It's an open pot of soup. You need to have a lid on this. So the closed system, that means really nothing's getting in and out of the system, but heat is exchanging with it, so it's not completely isolated. And then an open system, you can see all sorts of stuff can go into the soup and out of the soup. That would be an open system. One thing we need to define related to these systems is state functions. And this is kind of the path that you take to get to a system. So what we're trying to say here is that they always have the same value whenever the system is in the same state. And that should be somewhat obvious, is that if I have a pot of water at 50 degrees C and it's the same amount of water, it doesn't matter if I heated water to go from 20 to 50 or I cooled water to go from 100 to 50. All we care about is the final state, and that's going to be identical. So it's independent of path is what a state function means. And we'll elaborate on that later. The good example of this is that, change in altitude is a state function. The altitude of Murfreesboro compared to the altitude of the highest point in the Smokies Mountains that change in altitude is independent of path that you take. Okay, how I drive there. Ultimately, the altitude difference is the same. But the distance is not a state function because depending on the path I take, my distance will change. And that's kind of an example in a real world scenario. So as we look at heat flow, there's just two terms we need to get familiar with, and that is endothermic and exothermic. Exothermic is heat flowing out of the system, and endothermic is heat flowing into the system. Really need to say nothing more about that, just two definitions. You'll need to get a little bit familiar with the units. We'll be using joules and kilojoules and calories. And here's the conversion between joules and calories. We really won't use this much, but it does show you the base unit for SI. Okay, so now we introduced a term called enthalpy, and really for all practical purposes, enthalpy is just a fancy term that means the heat, the energy of the system at constant pressure. That's all it is. And for most part, that's typically what we deal with everyday life. So for us, constant pepper, yes, constant pressure is ideal. I mean, if you're talking about a reaction in your body, the pressure's not really changing much. Now, if you're talking about something in the lungs, yes, that pressure is changing. But if you're just talking about a reaction in your stomach, something like that, or a biochemical reaction, dealing with proteins or enzymes, anything like that, we can pretty much say that's constant pressure. And if you're doing something in the laboratory that's not in some sort of sealed chamber that's producing gas, it's going to be a constant pressure. So that's really all enthalpy is. And this is Q. This is what we use to designate heat. So it's just heat at constant pressure. So really we can now use enthalpy. The change in enthalpy is greater than 0, and the change in enthalpy is less than 0. This is going to be exothermic. endothermic, and this is going to be exo. So redefining those in terms of enthalpy. We can actually use subscripts next to delta H to tell you what type of specific process we're dealing with. And we'll see this on the next slide. So we can do different types of heat associated with reactions. You'll see that in a second. So for right here, for instance, what we're looking at here is we have different notations here, and what we're looking at actually is heat of fusion, which is melting. That's the word we use for melting here. It's a heat of fusion. We don't say the heat of melting. So this is the energy needed, if you will, to convert ice to liquid water. Okay, and it's per mole, obviously, because it's extensive property, so it has to be per some amount of material. And vaporization is convert the liquid water to vapor. One notice the difference in the magnitudes. It takes a lot more energy to go from liquid water to vapor water than it does to go from ice to liquid water. And that's because in this case, you're actually breaking all the bonds that associate the water molecules together, not the individual covalent bonds that hold oxygen and hydrogen together to form the water molecule, but what we call the intermolecular forces, which is chapter 6 we skipped, which we'll cover at the very beginning of Chem 11 and 20. The individual the individual bonds that hold the water molecules together and make it a liquid or a solid. So here you're not completely separating the water molecules. You're simply giving it enough energy for the molecules to slide past each other. Here you're actually separating all of those water molecules. And then, of course, the reverse would just be opposite in sign. So you can see we can use subscripts to define these different situations. Now, this is a heating curve. And this is kind of important here. So what we have here is a solid that initially is at minus 18 degrees C, and we're going to heat it all the way up to some temperature well above 100 degrees C. Okay, and you know that the boiling point is 100 degrees C, and the melting point is 0 degrees C. What we look at here and we see now is that as we add heat, the temperature changes. Okay, and we go from a block of ice at minus 18 degrees C up to 0 degrees C. So that heat that you're adding is going into the kinetic energy of the molecules. They're now moving more. Okay, and that's creating the motion in the molecules, but you haven't gotten to a high enough temperature to melt it. Then when you add more heat, the temperature doesn't change, and a lot of students have trouble understanding this. But if you were to have a pot of water at home boiling, and if you stick a thermometer in it, and you measure the temperature, it'll say 212 degrees Fahrenheit, 100 degrees C. You can crank up the heat all you want, that temperature will not increase. It will just boil faster. Now, if your thermometer is sitting on the bottom of the pan, you could see a temperature higher than 100 degrees C, and that's just due to the temperature at the bottom of the pan and the thermometer hitting. But if you suspend that thermometer in the water, you will not get a temperature higher because the energy is going in to actually now break into what we call phase change. This here is a phase change. It's going from liquid to solid. From solid to liquid. So the energy is going into that phase change, separating the molecules in a way that they can move past each other now. So effectively, the energy is going into affecting those bonds. Going from liquid to solid, that solid structure, that lattice energy has to be broken. Now you still have bonds associated with water molecules, and we call those hydrogen bonds, but they're not the same as that lattice energy bond in the crystal. And then you continue to heat, the water goes all the way up to the boiling point. Now, once again, it's going into the kinetic energy of the molecules, move faster and faster and faster and faster until they get to the boiling point. Once again, during a phase change, there is no change in temperature. The energy now is going to breaking those bonds and converting all of the liquid water into vapor water. And then you can continue to heat the vapor even further. And that would be adding more kinetic energy to those. That's easier to see now, the kinetic energy of those gas water molecules getting faster and faster and faster and faster. So you're superheating it. Heat capacity is, if you will, we can define as the quantity of energy needed to raise the temperature of an object by 1 degree C. And we're not going to use this as much because it's not defined in terms of any sort of amount of material. So it's kind of useless for comparing. So it's a general term of heat capacity. Hey, what's the heat capacity of a substance? How much temperature, how much heat does it take to raise the temperature of that object by 1 degree C? But it's not mass specific. So really, these are the two we'll focus on because you want to compare this two heat capacities of something. You want to compare the same amount of material. What's the heat capacity of a mole of copper or a gram of copper compared to a gram of tin? You don't want to use different amounts. So the only difference between these two is how they're defined. This one is in terms of grams, and that one's in terms of moles. And you could see there's different heat capacities for different substances, is what you would expect. And one thing you'll notice is that metals have very low heat capacities, and that's why we use them as for cooking. They have good conducting of heat. And one thing you'll notice is water has one of the highest heat capacities. At 25 degrees C, it's 4.18. And this is your units up here. So it takes a lot of energy to increase the temperature of water, is something that's important to realize here. So when heat is transferred from one thing to another, we can realize that there's going to be a negative sign associated with that. You can look at this as a way to kind of notate this, and that is when heat is lost from one thing, it's gained by another. Therefore, their signs are just opposite. This will become important as we calculate temperatures. So one equation we'll use is Q equals versions of this, mc delta T. This is the heat of a substance, can be calculated by knowing its mass, its heat capacity, its specific heat capacity here. So that will be this term right here, right here, specific heat. I'll just say SH, and your change in temperature. Right? And then, as long as you know those parameters, you can figure out how much heat is needed to change it to the temperature you want, or you can figure out how much heat went in to give you that temperature, or you can calculate a final temperature if you put in this much heat. And obviously, if you put a certain amount of heat in, it's gained. Well, it's lost from something else. The sign must be exactly opposite. What we'll also do is we'll look at ways in which we can modify this equation and not have to worry about certain things. So you'll see that in a second. So for one way we do this is calorimetry. And this is just a device for measuring heat change. That's all it is. And this is really what a fancy one here is, a bomb calorimeter. And you can see this unit here is all intact. You put your sample here, and then we can measure the change in temperature. Here's my thermometer. We have something to mix the water, make sure the heat is dispersed. We use some wires to ignite it. So this is how you can do like food calories. You could put a sample of food in here and measure how many calories are associated, because calorie is a measurement of that energy associated with that piece of food. And for this type of reaction, we're going to use a different type of equation that I'll introduce in class. And what we'll realize is that in calorimetry, well, I can show it to you here, and that is Q for a calorimeter is equal to the calorimeter's heat capacity, if you will, delta T. There is no M here because when I sample, this is the Q for the entire system that includes your every component of the system, the water and everything. And then what you do is when you get that number, you could put it in terms of moles of whatever substance you put in there. So if you put a gram of Snickers bar in there, you can convert that to a mole of Snicker bar, if you will. That'd be pretty difficult since we don't know what the molar mass of something like that is, but you get the idea. Next is standard enthalpies of a reaction. This is kind of what I introduced to you in the very beginning, is that, chemical reactions have enthalpies associated with them. And so I think I kind of really already covered this. I left this blank here to do it, but I did it in the beginning, is that um, if we have a couple reactions going to, I'll do it a little bit different here, and then say we have another reaction that has C plus E going to G, say for instance, you can sum up these reactions. Say you have enthalpy values for both of these. Let's say it's just 800 and 200. You can add these up. This would cancel out now. This is what you had to do for, might have to do for your lab. And your overall reaction now is A plus B plus E goes to D plus G. This enthalpy for this reaction will be negative 1,000 as you add them. So that's one thing we can do, and this is Hess's law. And that's what's shown here, how we can add these up, that H3 is simply equal to H1 plus H2 in this case. And that is the last slide for this video, and there's just a lot in this chapter. You need to make sure you look at this video before class and spend some time on this chapter.